Welcome back to the second video. In this video we are going to discuss some very important properties of radical expressions. Let's start with the concept of irrational numbers. Let's prove that the number cube root of 17 is an irrational number. You won't be proving this kind of concepts in calculus, but it's good to know the technique, the idea of proving that number is an irrational number. So we are going to prove this by contradiction. Let's assume that the cubic root of 17, this number, is a rational number, which means we can represent it as a fraction m over n. This is an irreducible fraction. If it's something simplifiable, we would have simplified that. So it's not a fraction in the form of 2 over 4. So you simplify this fraction, you get 1 over 2. So this is a fraction in its simplest form. Next step, I'm going to take the cubes of both sides to get rid of this cubic root. So take the cube and the cube of this number. And then this becomes 17 is equal to m cube over n cube. So if you multiply both sides by n cube, it turns out m cube is 17 n cube. So here comes the idea. The right hand side of the expression is 17 multiplied by something. So it's a multiple of 17, which means this left hand side of the expression is also multiple of 17, because these two numbers are equal to each other. So they have to be both multiples of 17, which means m is a multiple of 17. M is a multiple of 17. 17 times some k. Since this m over n fraction was in its simplest form, n is not divisible by 17. This side of the expression is divisible by 17 only. So only one copy of 17. 17 to the power 1. But this side, m cube, since m is divisible by 17, when you take the cube, m cube is going to be 17 cube k cube. So this side is going to be 17 cube k cube is n cube. So the right hand side of the expression has one copy of 17, the left hand side has 3 copies of 17. So which means this is a contradiction. So we can't represent this cube root of 17 as a fraction. So it's an irrational number. Let's simplify this expression. So here we have one very important property of nested square roots. So the property was the following. So let me start. So as always, as you do in parentheses, you start with the innermost square root. So let's start with the innermost square root. So the square root of 48, I can rewrite it as, so this part of the expression, only this part of the expression, pay attention only to this part. So it is square root of 13 plus 2 square root of 12. Now here comes the very important property that you are going to use several times, multiple times in your calculus course, is the following. So in general form, it's something like this. Square root of a plus 2 square root of b. You can simplify it as follows. Think of two numbers whose product is b, so this number, and sum is a. In our case, it's very straightforward. 12 multiplied by 1 is 12, 12 plus 1 is 13. So it means that this fraction is equal to square root of 12 plus square root of 1. My expression becomes 2 multiplied by, so what we have, 3, right? 3 plus another square root, 5, minus. Now instead of writing this 13 and 48, I'm going to write square root of 12 minus square root of 1 is just 1. So that gives me 2 under the square root 3 plus square root of, so now 5 minus 1 is 4. 4 minus, I'm going to rewrite this square root of 12 as 2 root of 3. So if you take the 2 inside the square root, it's 4. So that's 12. 2 root of 3. So I'm going to use that idea from the previous square roots again one more time. Now here think of two numbers whose product is 3. So that's again obvious. 3 times 1, 3 plus 1. But this time the sign between them is negative. So that's why my expression becomes root of 3 minus root of 1. So when it's a minus sign, you have to do the larger number minus the smaller number in order to get the positive expression. So we have 2 square root 3 plus, instead of this square root expression, I'm writing, so let's simplify this one more time. So I want to use that idea one more time, but I don't have 2 in front of the inner square root, so I need square root here as well. So that's why I'm going to take these 2 inside the square root, and when this 2 goes inside the square root, it becomes 4. So inside it's 4, and this 4 multiplies to 2 and this one. So now we have like 8 plus 4 root of 3. But I want 2, not 4. So I'm going to take 2 of these 4 inside the square root. So that makes my expression to be square root of 8 plus 2 root of 12. So that's my new expression. Now think of two numbers whose product is 12. So that would be 6 and 2. And sum is 8. So that's 6 plus 2. So this expression simplifies to root of 6 plus root of 2. Sum of two irrational numbers. So this is the simplest form of this expression. So if you simplify this, everything yellow expression, you will get root of 6 plus root of 2. The next thing is you should be very well familiar with the concept of conjugate of a numbers. Usually it's a number with square roots in our case. So the conjugate of this number is going to be square root of a minus square root of b. Square root of a plus square root of b and square root of a minus square root of b, these two numbers are called conjugates of each other. So if you want to rationalize the denominator, which means get rid of the square roots in the denominator, usually we don't want any square root or radical expression in the denominator. Everything should be in the numerator. In these cases, I will multiply both numerator and denominator with the conjugate. So that would be this expression. When you multiply the conjugates, the product of conjugates, using the difference of square formula, or you can use the FOIL and open the parentheses to verify this, but this expression is just a minus b. Difference of two numbers without square roots. So in our case, in the denominator, I will have 1 minus a. In the denominator, I will have 1 minus square root of a, because this expression multiplies to 1. So that's form of this expression where we don't have radicals in the denominator. Let's use this idea in the next problem. So here we want to simplify this expression. Before simplifying the expression, I want to rationalize the denominators of every fraction. Let's do it with a general form of the expression. The general form of the expression in our problem is 1 over square root of k plus 1 square root of k plus 1. A number and the number after that number, so plus 1. If I want to simplify this expression, I would multiply both numerator and denominator of this expression. So by k minus the conjugate, the denominator of expression becomes k minus k plus 1, and numerator is square root of k minus square root of k plus 1. When you subtract k plus 1 from k, it's negative 1. So this expression is negative 1. And when you divide this by negative number, you can just flip the order. So the result is square root of k plus 1 minus square root of k. So that's the general expression for our problem. You can treat this as a formula. This type of expression is equivalent to this one. So if I rewrite the first expression, so my first expression turns out to be root of 2 minus root of 1. The second expression turns out to be root of 3 minus root of 2. And the next expression obviously going to be root of 4 minus root of 3, and so on up to this last term, which becomes root of 100 minus root of 99. This root of 2 and minus root of 2 becomes 0. This root of 3 And the last problem with the radicals is this infinite nested square roots. So how to simplify this expression? So there is one very standard trick that we are going to use. Let's say this expression is equal to x. I'm going to denote it as x and take the square of both sides. If I take the square of both sides, this square will cancel out one of the square roots. So then I will have like 3 square root of 3, 3, 3, and so on is equal to x squared. As you can see from here, that this is still nested square root of 3's until infinity, so infinitely many times, which means that's still x. So because we denoted this expression as x in the beginning, so I'm going to replace that with x. Then I will have like 3x is equal to x squared. And since this expression is not equal to 0, I'm going to divide both sides by x. Then x is going to be 3, or like this. So if you do the square root of 3 and square root of 3, square root of 3 nested infinitely many times, that number turns out to be equal to 3. So this was our set of problems with radical expressions. See you in the next video.